Hello, and welcome to this presentation, Understanding Third-Order Intercept. In this presentation, we'll explain the meaning of third-order intercept and describe how third-order intercept measurements are made on both spectrum and network analyzers. Let's start by defining something called linearity. In the radio frequency world, linearity refers to the property of a device where the output of that device is directly proportional to the input. In other words, what comes out of a device is essentially a copy of what went into that device, although the output may be linearly scaled. Most devices are more or less linear over a certain input power range, but once we exceed a given input power level, the device becomes nonlinear. What happens when a device becomes nonlinear? One of the most important consequences of a device being operated in its nonlinear region, so to speak, is the device will generate harmonics and intermodulation products. Let's take a look at both of these. Harmonics are copies of a signal that appear at integer multiples of a fundamental frequency. For example, a signal at 100 MHz passing through a nonlinear device produces harmonics at 200 MHz, 300 MHz, 400 MHz, 500 MHz, etc. Although the fundamental is not often called the first harmonic, we do commonly refer to second harmonic, third harmonic, fourth harmonic, etc. Note that the amplitude or level of a harmonic decreases as the harmonic order or number increases. All nonlinear devices generate harmonics to greater or lesser degrees, and in almost all cases, harmonics are undesirable, and the amplitude of any harmonics should be kept as low as possible. Intermodulation products are also generated by mixing in nonlinear devices. Unlike harmonics, which can be created by a single input signal, at least two input signals are needed for the creation of intermodulation products. When these two input signals mix together in a nonlinear device, the output contains products at the sum and difference frequencies. For example, we input two signals or tones into a device, one at 250 MHz and one at 450 MHz. In addition to outputting the two original tones, our mixer will also output tones at the sum and difference frequencies, here 700 MHz and 200 MHz. Making this more complicated is the fact that not only will our two fundamental tones mix with each other, but they'll also mix with the harmonics generated by the device, such as 2F1 and 2F2, the second harmonics of F1 and F2. So we'll have additional intermodulation products at 2F1 plus F2, 2F1 minus F2, 2F2 plus F1, 2F2 minus F1, etc. We often talk about the order of harmonics and intermodulation products. Order refers to the sum of the unsigned coefficients. For example, 2F1, the second harmonic of F1, is second order. F1 plus F2 is also second order. The third harmonic of F1, 3F1, is third order. And, most importantly, 2F2 minus F1 or 2F2 plus F1 are third order products. Let's look at a diagram. The two fundamental or first-order tones can create a very large number of harmonics and intermodulation products. Second-order products include the two second harmonics, 2F1 and 2F2, as well as the basic sum and difference signals, F2 plus F1 and F2 minus F1. When it comes to third-order products, we have the third harmonics of the fundamentals, 3F1 and 3F2, and then the four additional third-order products, 2F1 plus F2, 2F2 plus F1, 2F1 minus F2, and 2F2 minus F1. These last two products are the most important. Why? In many cases, harmonics and intermodulation products are undesired signals. These products can leak into adjacent channels, create noise, distortion, etc. When intermodulation products are undesired, we call these intermodulation distortion, or IMD. Note, however, that not all intermodulation products cause problems. For example, the amplitudes of harmonics decrease as the order increases, so very high order harmonics can usually be ignored. And in general, higher frequency products will often be suppressed because they fall outside of amplifier bandwidths or filter pass bands. For the products that are still problematic, the typical way of dealing with them is through filtering, but this becomes very difficult when the products are very close in frequency to the desired or fundamental signals. Let's try to get rid of those unwanted harmonics and intermodulation products by placing a relatively narrow Gaussian-shaped filter over the fundamentals or desired signals. Most of the harmonics and intermodulation products fall outside of the filter bandwidth and are therefore easily attenuated or removed. However, two of the third-order products, 2F1 minus F2 and 2F2 minus F1 fall very close to the fundamentals, making it difficult to filter them out. So these two third-order intermodulation products are the ones that we're most interested in or most concerned about. In addition to being difficult to filter out, there's another complication when it comes to third-order intermodulation products. Namely, for every 1 dB increase in the fundamentals, that is the desired or useful signals, the undesired third-order intermodulation products increase in amplitude by 3 dB. In other words, the troublesome third-order products aren't just close in frequency to the fundamentals, but they also grow in amplitude much more quickly than the fundamentals. Looking at the slopes of the two lines, the fundamental and the third-order product, it would appear that these lines would meet at some point. That is, at some input power, the level of the third-order products would match, and eventually exceed, the level of the fundamental signals. In reality, however, this doesn't happen. Real-world devices have a limit on how much output power they can produce, regardless of the level of input power. Eventually, the max output power is reached and the gain lines flatten out. When this point is reached, the device is said to be in compression. We could, however, pretend that compression doesn't exist, and extend the two gain lines of the fundamental and the third-order product until they meet. The point at which they would meet is called the third-order intercept point, because this is where the third-order product power would intercept the power of the fundamental. It's important to remember that, strictly speaking, third-order intercept is a theoretical point that we calculate based on measured values. We can't measure third-order intercept directly. That said, many people do refer to measuring the third-order intercept of a device. So why do we measure third-order intercept? Third-order intercept is the most common way to quantify the linearity of a device. Often we're very interested in knowing how linear a device is, and third-order intercept is a simple and reproducible way of measuring linearity. The higher the third-order intercept, the better the linearity of the device, and the lower the level of intermodulation distortion that device generates. Device manufacturers use third-order intercept in their specifications and datasheets as a measure of linearity, although in many cases you will also hear the abbreviation IP3 used to refer to third-order intercept. We calculate or measure third-order intercept by sending two signals or tones into the device under test. These are usually closely spaced unmodulated or CW signals with equal amplitude. We measure the amplitude of these two fundamental signals or tones, as well as the amplitudes of the adjacent third-order products. Using the difference in power between the fundamentals and the third-order products and a simple formula, we can then calculate third-order intercept or IP3. Here's a view of the results of a third-order intercept measurement made using a spectrum analyzer. We see the four markers placed on our signals of interest, M1 and M2 on the fundamentals, M3 and M4 on the adjacent third-order products. And third-order intercept is automatically calculated and displayed using these values. Here our result is minus 16.853 dBm. Third-order intercept is a very simple measurement, but there are a few things we need to take into consideration when we make third-order intercept measurements. First, we need to be sure that we're measuring the intermodulation distortion generated by the device under test, not IMD generated by the signal generator or by the analyzer. There are two ways we can do this. We can minimize the generator contribution to IMD using something called source isolation. And we can use attenuation to check whether the IMD is being generated within the analyzer itself. And of course, instruments with good performance are necessary to get valid and reproducible results. The most common way of measuring third-order intercept is using signal generators and spectrum analyzers. It's easy to generate a two-tone signal using a single generator, but the proper test methodology for measuring third-order intercept requires two independent signal sources. We want to combine these two tones, but we also want to prevent them from mixing until they reach the device under test right before they're measured using a spectrum analyzer. In addition to using separate instruments to generate the two tones, we also want to be sure that the output signals from one generator don't find their way into the input of the second generator, creating intermodulation. We can isolate the source signals by using attenuators at the generator inputs, and/or by using a directional coupler, circulator, or isolator to combine the signals. On the analyzer side, we want to be sure that the intermodulation products we're measuring are not being created within the analyzer itself. Input attenuation is a simple and reliable way to determine where the IMD is occurring. The procedure is very straightforward. We add attenuation, usually about 10 dB, and observe the measured distortion level. If the distortion decreases after attenuation is added, the IMD is being generated within the analyzer. If the level of distortion does not change, the IMD is being generated externally. Let's look at an example. With zero input attenuation, we calculate a third-order intercept of -16.82 dBm. After adding 10 dB of input attenuation, our calculated third-order intercept remains almost the same at -16.682 dBm. So it's safe to say in this instance that the measured IMD is not being generated within our analyzer. We can also measure third-order intercept using an instrument called a network analyzer, which combines the functionality of a signal generator and spectrum analyzer. In this case, the network analyzer uses two independent, isolated ports to generate the two tones into the device under test. A separate additional receive port measures the third-order products and calculates the IP3. Careful reference plane and power calibration enables network analyzers to deliver highly accurate results, and most network analyzers include built-in source and receive attenuation. Using a network analyzer, we can plot the levels of the fundamental, third-order product, and calculated third-order intercept as a function of frequency. Markers can be used to obtain values at a given frequency. For example, the calculated third-order intercept at 2.5 GHz is -28.2738 dBm. We can see in this example that third-order intercept, and hence linearity, are decreasing as frequency increases. So in conclusion, devices being operated in their nonlinear region will generate both harmonics and intermodulation products. The combination of the fundamental signals and second harmonics creates third-order products, some of which fall very close to the fundamentals and are therefore difficult to suppress or filter out. Third-order intercept, also called IP3, is the standard way of quantifying the level of intermodulation distortion, and, by extension, the linearity of the device under test. Source isolation is needed for ensuring valid measurement results, and attenuation can be used to verify that IMD is not being created within the analyzer itself. This concludes our presentation, Understanding Third-Order Intercept. Thanks for watching.